All right, so anyone working in AI or ML these days, you've definitely run into this with large language models. They can figure out some pretty complex stuff. But sometimes it feels like they're using a supercomputer to add 2 plus 2. You know what I mean?
Yeah, definitely. And there's actually a ton of research going on right now trying to figure out exactly how to make these LLMs reason more efficiently. And this new survey really dives into the heart of it.
This deep dive is basically our attempt to break down this survey into something you can use. It's like a roadmap to what's happening at the cutting edge of efficient reasoning for LLMs and why it matters.
And it matters for a lot of reasons. I mean, we're talking about making these models actually usable in the real world, not just theoretical research projects.
Exactly. We want them to be fast, reliable, and to run even when resources are limited.
And this survey lays out 3 main ways that researchers are tackling this.
Let's break them down.
The first is by optimizing the models themselves. Tweaking the architecture and training process to get them to reason more concisely.
So making them think smarter, not harder.
Exactly. Then there's refining the reasoning output that they produce. So instead of just spitting out a ton of text, they can use more compact representations of their thought process.
That sounds pretty interesting, almost like getting them to think more internally.
Right. And then the third area is all about how you design the input prompts.
So like being really specific about what you want the model to do and how you want it to think.
Exactly. And sometimes a simple change in how you phrase a prompt can have a huge impact on the efficiency of the model's reasoning.
So this deep dive isn't about dumbing down the models or anything like that. It's about understanding how they work and finding ways to make them more efficient without sacrificing their power.
Right. What's really cool about this survey is it brings together a ton of cutting-edge research and shows how it all connects.
So before we get into the nitty-gritty of the different strategies, let's take a step back and talk about why efficient reasoning is such a big deal in the first place.
Okay, so we've all seen the incredible progress in LLMs over the past few years, right?
Yeah, it's been mind-blowing. They can write code, translate languages, generate creative content, all sorts of stuff.
Exactly. And a lot of that progress is thanks to the development of reasoning-focused LLMs, or LRMs for short.
LRMs.
Right, these are models that are specifically designed to perform complex reasoning tasks. Like, the kinds of things that require what we call System 2 thinking.
System 2 thinking.
Yeah, so it's the slow, deliberate type of reasoning that we use for things like problem-solving, planning, decision-making, stuff like that.
As opposed to System 1 thinking, which is more intuitive and automatic.
Exactly. So these LRMs, they've really pushed the boundaries of what's possible with AI. And a lot of that is thanks to innovations like chain of thought or CoT prompting.
Co-prompting.
Right. CoT was this breakthrough idea where you basically get the model to generate a step-by-step explanation of its reasoning process before it gives you the final answer.
So instead of just a single output, you get to see the model's thought process like it's working through a problem on a whiteboard.
Exactly. And that turned out to be a game changer for improving the accuracy of these models on more complex tasks.
It's like giving them the ability to show their work.
Exactly. And since then, we've seen even more sophisticated versions of CoT, like self-consistency CoT, where the model generates multiple reasoning paths and then kind of votes on the best one.
That's cool. So it's like having a team of AI experts all working on the same problem and comparing their answers.
Right, and then you have tree of thought and graph of thoughts, which introduce more structured ways of exploring the reasoning space.
So CoT and its variants have really pushed the boundaries of what's possible with LLMs, but there's a catch, right?
Yeah, there's a big catch. And you alluded to it earlier, this whole thing about models overthinking.
Right. It's like they're going off on these tangents. Sometimes you ask a simple question and you get a dissertation in response.
Yeah, exactly. They can generate these super verbose, sometimes redundant chains of reasoning, even for pretty straightforward problems.
It's like asking for directions and getting a lecture on the history of cartography.
Yeah, or asking what 2 plus 2 is and getting a whole explanation of basic arithmetic.
So why is this overthinking such a problem?
Well, for one thing, it's just computationally expensive. It takes a lot of processing power and time to generate all that extra text.
Right, which means it costs more to run these models and they can be slower to respond.
Exactly, and for a lot of real-world applications, that's a deal breaker.
Think about things like autonomous driving, where you need split-second decisions, or real-time conversational AI, where you can't have the model taking forever to come up with a response.
Or large-scale search engines, where you have millions of queries coming in every second.
So in those kinds of applications, efficiency is paramount.
And not only is overthinking expensive, it can actually make the models less reliable.
How so?
Well, the longer the reasoning chain, the more chances there are for errors to creep in. It's like a game of telephone. The more people you have whispering the message to each other, the more likely it is to get garbled.
So ironically, trying to make the models more accurate by getting them to think more can sometimes backfire.
Right. And it's a tough problem to solve because the way these models are often pre-trained seems to encourage longer reasoning as a path to correctness.
So it's not just about making the model smaller or using less powerful hardware, it's about fundamentally changing how they think.
Exactly, and that's where this survey comes in. It really lays out the landscape of efficient reasoning research and categorizes the different approaches that are being explored.
So let's get into the details, starting with the first category, model-based efficient reasoning. What's the basic idea here?
So the idea here is to fine-tune the LLM itself to make it inherently prefer more concise reasoning.
So we're not trying to change the output after the fact, we're actually trying to change how the model thinks.
Exactly, and one of the most promising ways to do this is using reinforcement learning, or RL for short.
RL, that's the technique where you basically train an agent by rewarding it for good behavior.
Right, and in this case, we're using RL to train the model to favor shorter reasoning chains that still lead to correct answers.
So we give it a gold star every time it manages to be both accurate and succinct.
Exactly, and the way we do that is by designing a reward function that takes into account both the accuracy and the length of the reasoning chain.
So a high score for a short correct answer and a penalty for being long-winded or just plain wrong.
Right, and the survey actually lists a bunch of different policy optimization methods that have been used for this, including things like PPO, GRPO, SIMPO, all sorts of acronyms.
Sounds complicated.
Yeah, it can get pretty technical, but the basic idea is to use RL to nudge the model in the right direction.
So what's the big advantage of using RL for efficient reasoning?
Well, the cool thing is that you can often achieve significant reductions in computational cost without really sacrificing the model's accuracy.
So it's like getting the best of both worlds.
Exactly. You're making the model more efficient without dumbing it down.
So it's a win-win.
Exactly.
Yeah.
And this has huge implications for making these powerful models actually usable in real-world applications.
Now, the second model-based strategy is called SFT, or Supervised Fine-Tuning, using variable length CoT data.
Right, so this approach is about training the model on a data set that contains examples of reasoning chains with different levels of verbosity.
So some examples are really detailed and some are more concise.
Exactly, and the idea is to get the model to learn how to adapt its reasoning length to the specific demands of the task.
So if it's a simple problem, it can be brief. But if it's a complex problem, it can go into more detail.
Right, and there are two main ways to create this kind of data set.
Okay, what are they?
The first is called post-reasoning CoT compression, where you basically take a really powerful LLM like GPT-4 and have it generate a full detailed reasoning chain for a bunch of problems.
So you're using the big guns to create the initial data set.
Exactly, and then you use another technique, either rule-based heuristics or even another LLM, to go back and shorten those reasoning chains.
So you're like an editor going through a manuscript and cutting out all the unnecessary words.
Exactly, you want to keep the core logic, but remove all the fluff.
And what's the second way to create this variable length CoBD data?
The second approach is called obtaining compressed CoT data during reasoning. And the idea here is to prompt the LLM to generate shorter reasoning from the get-go.
So instead of compressing the reasoning afterwards, you're trying to guide the model to be more concise during the inference process.
Exactly, and this has the advantage of being more natural and aligned with the LLM's own internal knowledge.
So it's like teaching the model to think efficiently from the inside out?
Right, and there are a bunch of different techniques for doing this, like learn to skip and token budget, which we'll talk about more later.
Okay, so once you have this data set with different reasoning lengths, how do you actually use it to fine-tune the model?
Well, there are a couple of main strategies. The most common is just called standard fine-tuning, where you use techniques like LoRa or full fine-tuning to minimize the loss on the efficient reasoning data set.
Loss meaning the difference between the model's predictions and the actual answers.
Exactly, and LoRa is particularly cool because it's really parameter efficient, which means you can adapt the model without needing a ton of extra compute.
That's always a good thing.
Yeah, and there's some evidence that models fine-tuned this way can actually generalize better to unseen tasks.
That's impressive.
And the other fine-tuning approach is called progressive fine-tuning, where you gradually reduce the target reasoning length over time.
So you're slowly weaning the model off its verbosity.
Exactly. You're like a parent teaching their kid to use their indoor voice.
That's a great analogy.
And this can be done by feeding the model shorter and shorter examples, or by progressively adjusting the generation process to favor more concise outputs.
So it's a more gradual and controlled way of making the model more efficient.
Right. So we've talked about making the model itself more efficient by tweaking its architecture and training process. But what about the other side of the equation, the output that the model actually produces?
That brings us to the second main category, reasoning output-based efficient reasoning.
Right, and this is all about finding ways to make the reasoning steps that the model generates more compact and efficient.
So instead of just working on the model's brain, we're also trying to improve its communication skills.
Exactly, and one of the most interesting areas here is this idea of compressing reasoning steps into fewer latent representations.
Latent representations, those sound like something out of a spy movie.
They kind of are. Actually, the idea is that a lot of the important information in the model's reasoning process is actually encoded in these hidden representations that are not directly visible in the text.
So it's like there's this whole secret language going on under the hood.
Exactly, and some researchers have even shown that just adding placeholder thinking tokens to the reasoning chain can improve performance, which suggests that these internal states are really important.
So it's not just about the words, it's about the underlying computations that are happening.
Right, and the idea behind compressing reasoning steps into latent representations is to basically find ways to capture the essence of those computations in a more compact and efficient way.
So instead of having to generate a whole paragraph of text to explain its reasoning, the model could just use a single vector or a small set of vectors.
Exactly, and that would save a lot of compute and make the model much faster.
That makes sense.
And the survey highlights a bunch of different approaches for doing this.
Like what?
Well, one approach is to train the LLM itself to use these latent representations during inference.
So you're basically teaching the model to think in a more compressed way.
Exactly. And there are methods like Coconut, or chain of continuous thought, which treats the final layer hidden states as these continuous thought tokens and feeds them back as input for the next reasoning step.
So it's like the model is communicating with itself using these compressed representations.
Right, and this has been shown to improve both accuracy and efficiency.
Then there's CoT, which uses a self-distillation process to learn continuous latent CoT, which means the model can do internal reasoning without even generating explicit textual steps.
Exactly, and CCO takes a different approach. It focuses on condensing long CoT into short continuous contemplation tokens using a dedicated compression and decoding module.
So there are all sorts of clever ways to make the model's internal reasoning more efficient.
Right. And then there's HIMA, which extends these ideas to multimodal LLMs, and Token Assorted, which uses a hybrid approach mixing regular text with discrete latent tokens.
And looped transformers, which show that you can effectively increase the model's depth without actually increasing the number of parameters by using these loops within the latent space.
Exactly. So we're seeing all sorts of innovation in how we can make models think more implicitly and efficiently.
So this whole area of compressing reasoning steps into latent representations is really about pushing the boundaries of what's possible with efficient reasoning.
It is, and it's a really exciting area of research.
And the second sub-area within reasoning output-based efficiency is called dynamic reasoning paradigm during inference.
Right, so this is a bit of a shift in focus. Instead of changing the model itself or its internal representations, we're now talking about making decisions about the reasoning process in real time during the actual inference.
So it's like giving the model the ability to adapt its thinking on the fly.
Exactly, and the idea is to use some kind of criteria to dynamically adjust the reasoning strategy based on the specific demands of the task.
So for a simple problem, it might use a very short reasoning chain, but for a complex problem, it might go into more detail.
Right, and this is in contrast to things like scaling up model size during training, which is computationally very expensive.
So it's a way to get more bang for your buck, computationally speaking.
Exactly, and the survey highlights a bunch of different train-free approaches that use various criteria to make these dynamic decisions.
Like what kind of criteria?
Well, one category is reward-guided, where the model uses a reward model to estimate how promising different reasoning paths are, and then prunes away the less promising ones early on.
So it's like a chess player evaluating different moves and discarding the ones that are unlikely to lead to a win.
Exactly, and methods like speculative rejection and reward-guided speculative decoding fall into this category.
Then there are confidence certainty-based methods where the model uses its own assessment of how sure it is about the answer to decide how much reasoning to do.
Right, so if it's really confident, it might just give a short answer, But if it's unsure, it might go into more detail.
And methods like dynamic parallel tree search, dinosaur, fast MCTS, and length filtered vote all use different ways to quantify the certainty.
Exactly. And then you have consistency-based methods like self-truncation best of n, which look at how consistent the latent embeddings of different reasoning paths are and decide to stop generating more reasoning if they're all converging on the same answer.
So it's like the model is saying, okay, we're all in agreement here, we can stop now.
Right, and that can save a lot of compute.
Now, the survey also mentions summarization-based dynamic reasoning. What's that about?
So this involves training LLMs to compress their intermediate thoughts into more concise gist tokens, as seen in LightThinker, which also uses sparse attention mechanisms for efficiency.
Gist tokens sounds intriguing.
Right, it's basically like summarizing your thoughts as you go along.
And IFTY takes this idea further with iterative reasoning and intermediate summarization, which lets it do really deep reasoning without exceeding the model's context window. Okay, so we've looked at how to make the models themselves more efficient and how to refine the reasoning output that they produce.
Right.
But there's one more piece of the puzzle.
Yeah, the input prompts.
And that brings us to the third main category, input prompts-based efficient reasoning.
Right, and this is all about how you can craft your prompts to encourage more efficient thought processes.
So it's like being a good teacher and giving the model clear instructions.
Exactly. And sometimes just a small change in how you phrase a prompt can have a huge impact on the efficiency of the model's reasoning.
So what are some of the techniques for prompt-guided efficient reasoning?
Well, one of the simplest but most effective approaches is just to explicitly tell the LLM to be concise.
So you could just add something like "be brief" to your prompt.
Exactly. Or you could set a specific token limit.
Like, answer this question in no more than 50 tokens.
Right, and the survey lists a bunch of different methods that use these kinds of prompts, like token budget or tail-eap chain of draft, concise chain of thought.
It's amazing how much you can influence the model's behavior just by changing a few words in the prompt.
It really is, and these prompt-based methods can also be used to collect short CoT data, which can then be used for fine-tuning.
So it's like a 2-for-1 deal. You get more efficient reasoning and you get better training data.
Exactly. Now, the other sub-area under prompt-based efficiency is called prompts attribute-driven reasoning routing.
Prompts attribute-driven reasoning routing. That's a mouthful. What does that even mean?
Yeah, it's a bit of a jargony term, but the basic idea is to use the prompt to route the query to the most appropriate LLM based on its characteristics.
So it's like having a triage nurse in an emergency room who decides which patients need to be seen by a specialist and which ones can be treated by a general practitioner.
Exactly. You don't want to use your most powerful and expensive model for every single query.
Right. You want to save those for the really tough cases.
And the survey mentions Anthropic's Claude 3.7 Sonnet as a potential early example of a hybrid reasoning model that seems to allocate more processing time to more complex tasks, although we don't know exactly how they're doing it.
And then there are research methods that train a classifier to do this routing, like RouteLM, which uses data from platforms like Chatbot Arena to learn how to dispatch queries to different LLMs.
And Sketch a Thought, which uses a lightweight router based on cognitive-inspired paradigms.
So it's like having a smart traffic controller for your AI queries.
Exactly, and uncertainty can also play a role in this routing process.
How so?
So some methods like self-ref actually fine-tune uncertainty specialized tokens within the LLM itself to help it decide when it might need to call in reinforcements.
So it's like the model is raising its hand and saying, I need help with this one.
Exactly, and then there's confident or seek stronger, which aims to train a model to predict whether a query should be routed based on calibrated data.
So it's like having a crystal ball that tells you which queries are going to be trouble.
Right. So this whole area of intelligent routing is really about optimizing the use of resources and making sure that we're using the right model for the right job.
It makes a lot of sense, and it's something that's going to become increasingly important as we deploy these models in more and more real-world applications.
Absolutely. So we've covered a lot of ground in terms of model architecture and inference strategies, but the data we use to train these models and the techniques we use to compress them are also really important for achieving efficiency.
That's a good point. And the survey dedicates a whole section to efficient data and model compression specifically for reasoning.
Right. And the first thing to highlight here is that the way we think about training data is changing.
How so?
Well, in the past, the focus has been on just getting as much data as possible. The bigger the data set, the better.
Right. More is always better.
But that's starting to change. There is a growing realization that quality is just as important as quantity, if not more so.
So it's not just about throwing more data at the problem, it's about being more selective about the data you use.
Exactly. And there are methods like Lemo which show that by carefully curating a small but high-quality data set, you can actually outperform models that were trained on massive data sets.
That's pretty amazing. Less is more.
Right. And Lemo focuses on selecting examples that are difficult, general, and diverse in terms of the knowledge domain.
So it's like a greatest hits collection of training examples.
Exactly. And S1 takes a similar approach, focusing on quality, difficulty, and diversity. And it also uses a technique called bucket forcing during inference to control the duration of the reasoning process.
So it's like setting a time limit for the model to come up with an answer.
Right. And then there's S2R, which explores the use of self-verification as a training signal.
Self-verification, what's that?
So it's basically getting the model to learn how to check its own work and make corrections.
So it's like having a built-in proofreader.
Exactly. And the cool thing about this approach is that it's really data efficient. The model can learn to self-verify with a relatively small number of training examples.
That's interesting. So we're seeing this trend towards being more strategic about the data we use for training.
Right, and that's important because it means we can potentially achieve the same level of performance with less data, which is good for both efficiency and accessibility.
Now, what about the other side of this coin, reasoning capabilities in small language models and model compression?
This is crucial for making reasoning models practical in resource-constrained environments like mobile devices or embedded systems.
Right. You can't exactly run a massive LLM on your smartphone.
Exactly. So researchers are working on ways to distill the reasoning capabilities of these large models into smaller, more efficient ones.
But that's not easy.
No, it's not. There's a significant gap in terms of what these small models are able to learn compared to their larger counterparts.
And this is known as the small model learnability gap.
Right, and the survey covers a bunch of different distillation techniques that are specifically designed to address this gap.
Like what?
Well, there's mixed distillation, which involves blending different types of reasoning examples during training counterfactual distillation, which augments the training data by masking out causal features, and feedback-driven distillation, which iteratively refines the distillation data sets based on the student model's performance.
Sounds complicated.
It can be, but the basic idea is to find clever ways to teach the small models the same tricks that the big models have learned.
And there are also approaches that use probing and retrieval mechanisms, encourage adaptive thinking during distillation, and even focus on internalizing symbolic knowledge into these smaller models.
Right, so there's a lot of innovation happening in this space, and it's really exciting to see what's possible with these small but mighty models.
Now, what about more traditional model compression techniques like pruning and quantization? How do those affect reasoning?
So quantization, which is basically reducing the precision of the model's weights and activations, actually tends to preserve reasoning performance pretty well.
That's surprising. You'd think that making the model less precise would make it worse at reasoning.
Yeah, it's counterintuitive, but it turns out that the model can often compensate for the reduced precision without too much of a performance hit.
So that's good news for making these models more memory efficient and faster.
Exactly. However, pruning, which involves removing parts of the model's parameters, often leads to a more significant degradation in reasoning quality.
So you have to be more careful with pruning.
Yeah, and another challenge with all these compressed models is making sure that they can still effectively follow instructions.
That's important if you want to be able to use them for a variety of tasks.
Right. Now, the final piece of the puzzle that this survey covers is evaluation and benchmarking.
Right, because we need to have a way to measure how well all these different techniques are actually working.
Exactly, and the survey highlights a few key benchmarks and evaluation metrics.
Like what?
Well, for inference time computation, there's a SIS-2 Bench, which evaluates LLMs across 5 different reasoning categories using a diverse set of data sets.
So it's a pretty comprehensive benchmark.
Yeah, and it's designed to give you a good sense of how well a model performs on a variety of reasoning tasks.
And the survey also mentions some ongoing studies that are looking at the impact of various inference time optimization techniques and test time scaling, or TTS.
Right, and one of the interesting findings from these studies is that the optimal TTS approach often depends on specific factors like the characteristics of the model and the difficulty of the problem.
So there's no one-size-fits-all solution.
Exactly, and the survey also mentions a novel overthinking score, which is a metric for quantifying how much overthinking a model is doing.
That sounds useful. I mean, we've been talking about overthinking as a problem, but it's good to have a way to actually measure it.
Yeah, and the interesting thing is that the researchers who developed this metric found that strategies for mitigating overthinking can actually lead to both improve performance, and reduce computational overhead.
So it's a win-win situation.
Exactly. And the survey also touches on some research that's looking at the effects of very long CoT reasoning and the design of reward functions that can encourage more stable and concise reasoning.
So there's a lot of interesting work being done in this area.
Yeah, it's a really active area of research, and it's moving really fast.
So for our listeners out there who are working on or just interested in efficient reasoning in LLMs, what are the key takeaways from this survey?
Well, the main message, I think, is that this is a really important area of research with a lot of exciting potential.
It's about making these powerful models more practical and accessible.
Exactly. And the survey lays out a really clear roadmap of the different approaches that are being explored.
And it highlights the need for continued research in this area.
Right. And the survey authors also pose a few thought-provoking questions about the future of efficient reasoning.
Like what?
Well, one question is, what are the limits of latent reasoning? How much can we compress the model's thought process without sacrificing performance?
That's a good question. And another one is, how can we develop more robust and generalizable methods for routing queries to the most efficient model?
And can we find ways to combine the strengths of different approaches like RL and SFT to achieve even better results?
And how do we ensure that these efficient models are also safe and reliable?
Right, and what new benchmarks and evaluation metrics do we need to develop to keep track of progress in this field?
So there's still a lot of work to be done, but the future of efficient reasoning in LLMs is looking bright.
It is, and I'm excited to see what new breakthroughs emerge in the coming years.
Me too. Thanks for joining us for this deep dive into efficient reasoning in LLMs.
My pleasure.
And for those of you who want to learn more, be sure to check out the survey paper and the accompanying repository of resources.
There's a lot of great information there.
And until next time, keep on learning and exploring the fascinating world of AI.
See you next time.